Are you back? Maybe I'm
Yeah.
early. Yeah, okay. At least one of you are back. Then now let's see. Recording is on. Yes. So the use of these logarithmic diagrams give sort of argument for actually using the average value of the existence area as the condition that will be obtained in a solution of fluoride ions or in a solution of hydrofluoric acid. And this is valid actually for, I mean, it's not obvious that it's any advantage with a simple compound like HF or a simple compound like fluoride ions, that they can be calculated as well. But we'll see with a more complicated system like phosphates for phosphoric acid. This is a figure from the book. This is a fraction curve of phosphoric acid that below pKa1 phosphoric acid exists as exactly the free proton acid. Above pKa1 it exists as H2, the single deprotonated species. Then it's another pKa value, and it's a double deprotonated species, and a third pKa value, and a triple deprotonated species. We can speak about the phosphoric acid system, or possibly simply the phosphate system. Phosphate is literally this ion, but the phosphate ion is connected to the hydrogen phosphate and a dihydrogen phosphate and phosphoric. So in the respect of if you put an phosphate ion in a solution and in an environment, depending on the pH, this phosphate ion will be protonated a little bit or even more. The use of fraction curves, they are very useful because they are quite illustrative, and you can actually use them quantitatively around the pKa values, but maybe you can't do express anything about a species that has an existence area in the acid part. Then you can't do any conclusions about the phosphoric acid in this respect in the basic environment here. In order to do that, you need a logarithmic version, and that is no problem to construct such a diagram. It's just a lot of algebra, but there exist very efficient computer systems freely available, and I thought we should introduce one of those during the afternoon maybe. It's called Medusa. There are other similar softwares also, but we start with Medusa. A question. This is the hydrogen carbonate or hydrogen carbonate system, or it's the carbonate system if you wish to speak about carbonate ions, or it's the carbonic acid, or it's the carbon dioxide system. There are four different names of one and the very same acid-base system. For example, hydrogen carbonate is present in seawater, and it's probably the main buffer substance in seawater. What is the pH in seawater? Then seawater, natural seawaters, they have pH slightly above 8, indicated by this light blue rectangle here. So the seawater is actually actually dominated by the hydrogen carbonate. There are a slight tendency of carbonic acid in seawater, not enough for the seawater to start to bubble. But there is a little bit, according to this diagram, if the model is describing the seawater correctly, there are a few percent carbonic acid and also a few percent of carbonate ions. And you can, of course, ask, why is it important? Why spend such a lot of effort to understand such systems? These carbonate ions, they now let's see if I draw them here. Pen on, pen. They are somewhere in this region. So maybe the pH of your seawater is here. There is 1% of carbonate ions. Is this of importance? And I would like to say yes, because if the pH of the seawater is decreased, say 1 unit to pH 7, it would still not be acidus in some respect, but the amount of carbonate ions would essentially not go down to 0.1 or lower. What does it matter? It doesn't matter for humans. We can still bath in the sea and such things, but for every possible seashells creature, they would be tiny and less able to live in water. So acidification of natural waters is a threat towards everything that uses calcium ion and carbonate ions to build shells. And this is quite common. Very many creatures living in sea that fishes feed on, for example. They build plankton and such things. They build shells with calcium carbonate. If they can't do that, they are easier victims for fishes, and then fishes are not very nice creatures, so they will eat them all, and then they will starve, and we won't be able to have any fish for lunch or something like that. We'll see what happens. But from a chemical point of view, using this simple predominance diagram method, one can calculate the pH of seawater. This fraction diagram is perhaps not very helpful in that respect. We see that it is somewhere, since we have, if we assume that we know that we have mainly hydrogen carbonate in the water, it has to be somewhere here. We can do it more thoroughly. We can determine that the total concentration of the hydrogen carbonate is something like millimolars in the water. Then the minimum pH and the maximum pH would be something like 3 and 11 of any acid base with that concentration. So here, well, the maximum and minimum is not close to the borders of the hydrogen carbonate existence area. So we can simply just take the pH of a solution of hydrogen carbonate is the average value between the limits of that area, the green area here, that is 8.35, and which is quite reasonable. It's quite accurate. If you measure the pH in the sea, you will be within 0.1 units of this, hopefully. If you measure the pH in Lake Baltic, you may be finding a lower pH value, but not a lot lower, not yet at least. But the pH, the sea is actually decreasing, suffering from a decreasing pH. Even the oceans around Antarctica, I read about for a few days ago, has decreased a few hundreds of a value, a pH value. It's not a lot, but I mean, it's the only sea that we have, at least down there in Antarctica. It's deep and it's cold, and it's a lot of fish and stuff are growing there. Could be of importance. It's at least here for this course, it's simple way of calculating pH of a hydrogen carbonate solution. If you want to do this analytically, usually it is not given in textbooks in chemistry. If you treat the hydrogen carbonate as an acid, then you would calculate, then you would calculate the pH as something like 6.65. And this is not at all equal to 8.35. So you can't only use it, treat it as an acid, because it's not only an acid, it's also a base. Well, let's check it as a base. Then you would find a pH value of 8.7. This is better, but still a little bit wrong. However, if you treat it as an ampholyte, that is a compound that acts both as acid and base, then you will obtain a pH of 8.31. And this is very okay. 8.31 is approximately similar to 8.35 that we had on the previous picture here. Which one is the most correct? Yeah, maybe this one, or maybe none of them. But I mean, you need to do these calculations to take into account both the basic character of the hydrogen carbonate and the acidus character of the hydrogen carbonate. And then the expression for this hydrogen ion concentration is a lot more complicated, even though we only take into account one step forwards. You can do some approximations, and you can come to a statement that the hydrogen ion concentration should approximately be the square root of the product of the neighboring acidity constants, and on a logarithmic scale, it's the average value of the pKa values, same as we used here. But yeah, if you have a computer algebra system, then it's no problem to obtain this expression, or even a lot more complicated expressions. But I mean, they won't give a lot of understanding. Algebraic expressions are good for calculating things, but they don't contribute a lot to what do they mean. Yeah, it's difficult to state. Well, we leave the ampholytes and coming back to acids. This blue curve is a typical titration curve of a two protonic acid, and we can define this buffer capacity as the ability to resist change. Say if we look here, if we add some hydroxide ions, then pH is not changed a lot. So the buffer capacity is high here. While at the equivalence points, the slope of the line of the titration curve is very steep. So here one would say that the buffer capacity is low. If we add a little bit of hydroxide ions, then we introduce a large change of pH. Not to speak about that thing here at the second equivalence points, it's much more sensitive at this point. But here in between, the buffer is high again. So the red curve here is actually indicating the buffer capacity, and we can there are some automatic system that checks whether you are at the equivalence point or if you are at the half titration point. So we can say that at equivalence points, the buffer capacity is a minimum, and at half titration points, the buffer capacity should be a maximum. And you see here in this, the second pKa point, the buffer capacity is definitely a maximum, and it's definitely a minimum around the equivalence points. That we don't see any maximum here is dependent on the fact that also water buffer, water and hydrogen ions form an acid-base pair, and at low pH values, at least here in this region. Otherwise, if we would have done this titration in another type of solvent where we wouldn't have had water present, then I think we would have seen such tendency here. The book introduces something called proton affinity. In gas phase, and also in solution, one could speak about proton affinities. And let's see if we can see any tendency here. Now let's see, pen on. HCl, you do know that as a strong acid. It has this gas phase proton affinity. Now let's see, AP is the gas phase and A prime is the effective in water, yes. So let's, typical strong acid, typical weak acid is water. What is the proton affinity? It's a considerably higher value in gas phase and slightly higher in water, but it's at least higher. So we can draw the conclusion that a weak acid has, if we interpret this proton affinity, what is an affinity? It's unfortunately not any thermodynamic quantity. It's not a jump from, say, the A minus and the H plus going down to the compound like that. Here they, in this diagram, they introduce another type of quantity, proton gain, And I would say that delta proton gain of H is the negative of delta proton affinity, delta H proton affinity. So affinity is how much do a species like to attract something, but proton gain is directly a statement that a proton is attached to, for example, the A minus here. This is similar. Proton affinities is perhaps used in the book for describing and discussing molecular properties, that how much energy is gained for when binding a proton. You do, I think, know it from electron affinity. Oh, sorry. The ability to attract electrons. This is more or less the negative of the delta H electron gain, and the addition of electrons. But maybe this will be back in tomorrow. H3O plus is a strong acid. It has a very low proton affinity. I mean, this compound, the H4O2 plus, has been looked for, but not found, I think. So there is no reason to assume that an H3O plus should have a proton affinity 723. I don't know how this is calculated. It is probably calculated, and the similar value 1130. It's at least less, 50 kilojoules per mole less than the water molecule in water solutions. And you can make a diagram from, say, you can make a diagram from, say, the neutral molecule. Breaking the bond requires energy. Ionizing one of them requires some energy, the hydrogen, and then this neutral gas phase, soon to be base, attracts the electron. This diagram indicates that it requires energy. Yeah, electron gain is perhaps a positive value when the electron affinity here is, I don't know the scale here. It can't be energy since it's continues upwards here. Most neutral gas phase atoms, for example, have a positive electron affinity and thus a negative electron gain. So it should be a little bit downwards, but maybe this is an artist representation. So there are still a few errors left in the book, I think. But we arrive at some higher energy state for H plus and A minus, and then when the proton recombines, then it's a way to this is a way to illustrate this recombination between proton and negative species here. So what determines the strength or of a base or an acid? Just a moment. It is essentially two variables called in these two graphs. They're called the electrostatic parameter, charge approximately. Here there are single charged anions, double, triple, and here is Gibbs energy of hydration. Is it negative value of Gibbs energy of hydration? What does it mean? 3000. This is or times 1000 kilojoules is nearly 3000 kilojoules to be gained if phosphate ions from gas phase hydrates, and then that means that it would certainly attract and form strong bonds to the solvent water. This could be viewed as the ability for the phosphate ions to act as a base. It is quite large, but I don't think they have been speaking about that. In this diagram, they mainly focused around the charge here. Single charged ion, weak bases, less strongly bound, but still they are bound to water. They are hydrated. Same idea could be given with positive ions. If you have low charged positive ions, do they bind water very strongly? Here is on this axis is pKa for the water complex. pKa 14 and higher means that these low charged ions, they're not at all that acidus. But on the other hand, if you take highly charged ions, they are strong acids actually. We'll see. Can have a whiteboard. A metal ion, say aluminum, 3+. It's easy to see that this is an acid because it's charged. So it's definitely a Lewis acid because it's electron pair acceptor. But it's also one can visualize it as a Brønsted acid. Suppose this complex is surrounded, the aluminum ion is surrounded by, say, 6 waters. There is no reason to choose 6 except that octahedral coordinations are quite common. Then the aluminum could attract at least some of the water molecules, so some of them would lose an atom, a hydrogen ion, and decrease the charge and then release hydrogen ions like that. So this is possibly a simple expression for showing that charged atoms, charged ions, positive ions are in water solution are able to work as Brønsted acids. Smaller, less charged acids, they do not necessarily release any hydrogen ions. So this is just a statement, single charge, hardly acidus, 3 or more, 4+ is perhaps occurring sometimes. It's very, very strong acids. 2+ is borderline, so we don't know how to distinguish them easily. And this is actually shown here also in this diagram. You see that there seems sodium, magnesium, and well, we don't have aluminum here. Where is aluminum? It should have been somewhere here, I think, on this line here. What about, why is this thallium, scandium, lutetium, iron? What's so problematic with them? Why are they seems to be more acidus than from the charge? I think one can explain that by the higher effective charge. All of these, magnesium is a noble gas configuration, and aluminum 3+ would also be a noble gas configuration. But iron is a transition metal, and thallium is a transition metal. Well, it's not a transition metal, but it is a metal far down in the periodic system, so it has a lot of d electrons and f electrons inside, so it has less efficient shielding effects. So it will obtain a higher effective nuclear charge. Higher charge, thallium 3+ is perhaps acting like if it would be 4+ or 5+ as an equivalent noble gas ion. This is also a reason why copper is kind of acidus ion, and mercury and tin, they are mercury is in the transition metals. Tin 2+ is well, two positions away from the transition metals, but high effective nuclear charge, I would say. Doesn't explain fine details in this variation. There could also be contributions from covalent bonding to the environment, to the ligand water molecules, for example. When it comes to bases, simple rule is that higher charge is stronger base, and there are not so many highly charged bases. Suppose you have OH minus, but if you compare it to O2 minus, then it's definitely so that the higher charged version is a lot, at least 10 orders of magnitude stronger base. But for oxo anions, it's easier. You can have this. These are oxo acids, so HOCl that would correspond to OCl minus. Is it a strong acid, or is it a strong base? Well, on average, maybe we can see, we can compare to this one. This is carbonic acid. Why doesn't it has any chlorine? Carbonic acid. Here is chlorine. So ClO2 minus. The acid is a stronger acid than the single oxygen acid. That means that the base here is a weaker base than the single oxygen base. And that, an easy way to explain that would be just size. This is a small molecule with a 1 minus. This is a bigger molecule with a 1 minus. And do we have here we have the chlorate. The acid form is very acidus. The pKa is -1, but the chlorate ion should be a very, very weak base. What's the difference between hypochlorite, chlorite, and chlorate ion? It's the size, essentially. So spreading out the charge over a large ion make it a weak base. Well, this table actually shows the oxo acids, and you can calculate the approximate value of how strong an acid is. An oxo acid is something that contains either oxo and maybe some OH, and in various proportions. If P is the number of oxo groups, then we see here is no oxo group. Then we have a weak acid. If we have one oxo group, then it's a slightly stronger acid. 2 oxo groups is quite a strong acid. This is very strong. 3 oxo groups, do we have that here? Perchloric acid, very, very strong. So you can sort of distinguish the first pKa by claiming that it is these, I think, pKa values are probably experimentally determined, but you can calculate that by 8 minus 5 times the number of oxo groups. Here it should have been 8. 7.2 is more or less equal to 8. Here it's 1. 8 minus 5 times 1, that is 3. Yeah, this fits. P equals 2. 5 times 2 is 10. 8 minus 10 is -2. This fits. 8 minus 3 times 8 minus 15 is, no, let's see, my calculations minus, yeah, I mean, the trend is at least a lot indicating. If you would plot these pKa values as a function of the number of oxo groups, I think you would get a fairly straight line feature. In some cases, there are several oxo groups, hydroxy groups. So this is in principle a 4-valued acid, but since it's very weak, then it's maybe not easy to get rid of more than one hydrogen ion. If we take, do we see something that we can recognize? This is sulfuric acid. So of course, one of the hydrogens, it's very acidus, but then when you come to the hydrogen sulfate ion, that we don't have. Unfortunately, we have, no, this is phosphonic acid, yeah. You can estimate pK1 and then pKa2, etc. This is only for the first. This expression is for the pKa1, and then add approximately 5, I think, to get the next of the pKa values. So if this would be, if pKa1 would be 10 for the tetrahydroxysilane here, so pKa2 would be 15 then, and this is outside area of water. But here, the tellurium hexahydroxy, if it's 7.8, and then the second one is 11.2, it's approximately a difference of, we can round it to 7, and then we up round this to 12, and then we get 5. This is only a very approximate values, but still kind of interesting trends, at least in the oxo acids. Also, the basicities of the oxo anions follow similar rules. I think they call this Pauling rules. Of course, Linus Pauling was very active in very many years, all of 1900s, 20th century, more or less, the main part of it. So there are a lot of things that are due to Linus Pauling. Now let's see, time is running, 11:52. We can soon, I will end. We can also speak about basic acid and basic properties of oxides. Here in this diagram, suppose we have Ashto. Sorry. Here we have, for example, sodium oxide. How does it react? Well, we have sodium plus as an acid, and we have oxygen 2- as a base. And the oxide ion is very, very strong base. So I would say that this is a basic oxide, and thus they colored it by one color. So in the beginning here of the periodic system, the positive ions are less strong acids than the oxide ions are basic. So the acid-base character of these oxides are dominated by the basicity of the oxide ions. Later, suppose aluminum, then we have silicon, phosphorus, sulfurous. We can look at the sulfur. There we would have what is the oxide of sulfur? It's the SO3, for example. And we can see this formally as a 6+ and 3 times oxide ions. And even though the oxide 2- is a very, very strong base, stronger than you can have in water. So the sulfur 6+ is well, perverted strong acid. So it's much, much stronger acid than the free oxide ion. So this is termed as a acid oxide. And in between here, we have, for example, aluminum, where the aluminum 3+ as an ion and the oxygen 2-, they sort of balance each other. And it's difficult to find any clear acid-base character of aluminum oxide. Maybe it can dissolve in acids, thus acting as a base. Maybe it can, acting as an acid, I mean, dissolving basic environment. Maybe it can act as a base and dissolving acid environments. It's an amphoteric oxide. It needs to be between, if we change character from basic oxides to acidic oxide, there should be some amphoteric in between. And there is a border area sort of in the periodic system. And it depends, of course, which oxide. Aluminum oxide is more or less only occurring as aluminum 3 plus and oxide 2 minus, but lower here, arsenic and antimony, tin, for example, there are several different oxidation states available. And that also, of course, indicates some effect on the properties. You can see that from the transition metals here, transition metal oxides. So the low charged, the low oxidation states, the 2 plus oxides, for example, in the beginning, they have basic properties, while copper oxide and zinc oxide are termed as amphoteric. If they're not basic, then after basic comes amphoteric, and this is valid here also. But what happens when in the center of the transition metals, you can have some higher oxidation states? Increasing oxidation states means increasing the acid character of the cation in the oxide, if you see it as an ionic compound at least. And the high 5 and 6 and even higher oxidation states act as acidic oxide. Now let's see, I don't see this. Chromium and manganese 6 plus, for example. CrO3 is a very, very acidic oxide. Sorry, resume sharing. CrO3 is a very acidic oxide, while CrO or Cr2O3 do have some basic character. I would move this Cr2O3 as amphoteric, actually. Maybe not. So this is of importance, for example, share. So if you have a basic oxide and basic oxide and an acid oxide, SiO2, you can get concrete, a mix. It's a chemical compound between a basic and an acid oxide. You need some water also, otherwise a dry piece of calcium oxide and a dry piece of silicon oxide, they won't react. But here you get the compound. And in reality, you can mix in a lot of silicon oxide, because this is cheap sand. So then use this to make concrete and build houses and such things. So this is acid-base, an application of acid-base theory. Some of these highly charged ions, highly charged metal ions or central ions, whether it is phosphorus or it's a transition metal. They can polymerize these anions. But then we come to Lewis. Maybe the clock is 12 o'clock now. I think we should make a break. I have a few images left, and then we can postpone this to afternoon. Is it okay with an hour lunch or something like that?
Yes.
Okay, then sorry.